So now we want to give some example on regions that not necessarily on solids that not necessarily always are simple in each direction. And so the first thing is, and the question is asking, find the volume of the solid bounded by the surface x equal to y squared. So if I look at the x and y, the relationship between the two of them is going to be basically a little bit going this way, a little bit going that way, and it's going to be x equal to y squared. It's a parabola that opens up toward the x-axis. And then if you think about this, this is really like sort of an opened up cylinder going about that. It's like if you had a piece of paper, you can wrap it around this area, and then you get and make a cylinder basically out of that. That's this function. That's that surface. And then you have the z equal to x equal to z, which is a plane that goes out from the origin, and basically if you look at it, it's going to be a line on the x and z plane. But when it cuts through the cylinder that we have, it kind of cuts through it a little bit that shape. And then we have also x equal to 1, which is a plane that goes through this. So the entire shape of the cylinder, entire shape becomes and this way. And then you have a z equal to 0, which is the bottom of that. So this is the shape that we drew. See this, the blue is the cylinder, but it was cut by a plane in red or pink, and then the plane kind of leaves a little bit of a curvy shape, and they cut edges. And then this is the plane x equal to 1, basically. That cuts the other one, and the bottom is the z equal to 0. Oh, look at this one. And again, red is the x direction. If I want to compute, is this going to be simple solid in the x direction? No, it's not a simple solid, because x simple solid, because if I'm going to x direction, sometimes I'm starting from the blue surface going all the way to green, sometimes I'm starting from the red surface going all the way to green. Henry said that if we look at the region and in the x direction, sometimes we come from this wall to this basically filled rectangular region, and sometimes we come from that plane to this rectangular plane and rectangular part of the plane. So x direction is not simple, and I want to use either y direction or z direction if I want to make it a little less complicated for me. So let's set it up, and then it's important to know how to do non-simple regions. But if you sometimes also choosing the simpler region is simpler solid is the easier way to go. Now I say let's do just the z direction is inside. If I go with the z direction inside, z equal to 0 is the bottom part, and z equal to x is the top part. See, z equal to x and z equal to 0 is given. So I'm setting it up, z equal to 0, z equal to x. And then the integrand is going to be, we're finding the volume of the solid, so it's going to be 1, and then this is dz. And so now I have to figure out the two outer integrals. And how do I find the two outer integrals? Let's see. The projection of the solid over the projection of the solid over xy plane, which is the plane of the two other variables, it looks like a parabola. We actually drew that one first when we were trying to figure out the shape. And so that's the shape. So if I draw it, this is x, this is y. It's a parabola x equal to y squared. And so it looks like that basically. And then we have x equal to 1 on top of that. So it's going to be x equal to 1 on top of that. This one is x equal to y squared, and the other one is x equal to 1. And so it just seems like I would like to go in this direction. And so x is going to be between x equal to y squared and then x equal to 1 basically. So this one is x equal to 1. This one is x equal to y squared, and the other one is x equal to 1. So y squared and 1, and I know dx. So the most inner out of the two outer are dx, dy. So dx is the second inner, and then dy is the most outer. Now, where does y end? I have to find y value for this point and y value for that point. And if I intersect both of them together, we'll see this is between -1 and 1. And so when I integrate now, out of this one, I will get the value z run from x 0 to x, which is going to be x, and then I have to integrate with respect to x, and I get x squared divided by 2. Plug in those values. I'm going to get, out of this, I'm going to get 1/2 minus and y to power 4 divided by 2, and then I have to integrate that with respect to y and find the final, and the final answer is going to be 4/5. Now, another question, how do we find w, and that's the solid, and that is the region inside the unit sphere, x squared plus y squared plus z squared equal to 1, and above the plane z equal to 0, and below the plane z equal to y. And so let's see what GeoGebra tells us. That's the sphere, and if you move the sphere around, and so if you move the sphere around, the red plane is the plane. This is the y-axis, and that's the z-axis, and the red plane is z equal to y, or y equal to z. And then the other thing that you have is the blue plane, which is z equal to 0. So the two plane, basically, if you think of the sphere as an orange, the two plane are slicing the orange into one wedge. So what you're trying to figure out is you're trying to figure out the area in the volume of that little wedge of the orange. So now to find the basically that volume, what we need to do is, or if we are trying to find how to set up the integral, we have to look at the wedge. And what I see is in the z direction, if you look at the wedge that we drew in GeoGebra again, in the z direction, it's not quite simple. So how do I set up in either direction, either x direction or y direction or z direction? So if you really want to have a simple region, y direction is going to be a simple region, and y in the inner part. But we discussed that sometimes we have to figure out how to set up non-simple regions, because some regions, in this case, there is a way to find a simple region, but some simple solid, but some solids are not in either direction simple. So how do I set this up in the non-simple direction, which is a z direction? So if I go with a z direction, then what happens is that I have to figure out the projection over xy plane, which the projection over the xy plane is just that the sphere over here, and then it's just going to be the intersection of the sphere with the xy plane, and it will be cut off at the x plane. And so now that's the region. But if I set it up that way, I see that some part z ends with this plane, some part z ends up with this sphere. So I have to figure out which part is which. And that's not too difficult. I can actually plug in z equal to y inside the plane, and then through that solve for where the plane is not it is splitting, but the solid is splitting, and so that's the way to go. So again, we're gonna divide the solid into two pieces. One piece is going to be the upper part is y. The other piece, the upper part, is the sphere. One piece is the plane z equal to y, so z equal to y, and the other piece is z equal to square root of 1 minus x squared minus y squared, which is the upper half of the plane. So the two pieces in there. And so how do we choose which is which? And it turns out that if I plug in z equal to y and I solve, I get x squared plus 2y squared equal to 1, which is going to be an oval, and that is where the bounds are happening over here. And so this is the shape. This is the x squared plus 2y squared equal to 1 when you plug in z equal to y into here. And over the orange area, the little wedge is sitting between z is sitting between 0 and z equal to y, and then between the other area, z is sitting between 0 and then the upper half of the plane. So we have to find this region. This region, the orange region, is when x is between -1 and 1, and y is between 0 and when you solve x squared plus 2y squared equal to 1, you get this. And here is D2, which is the pink part, and y is sitting between that and this, and x still going between -1 and 1. And so, and then you set up the integral, and integral is going to be equal to the double integral and the triple integral, and the inside one goes from 1 on D1 goes from 0 to y, on D2 goes from 0 to the upper half of the plane for, and this is when z equal to 0, z is equal to y, and z equal to 0, and z equal to the upper half of the square root of 1 minus x squared minus y squared. And then you have to notice the outer parts. Outer parts are just setting up how we set up the regions. This is region 1, D1, and this is region D2.